900 feet. That is how high the lava fountained above the floor of Halemaumau crater on the morning of the 23rd of April 2026, when Kilauea's 45th eruption episode of its current phase split the Hawaiian sky before dawn. 900 feet of liquid rock fired vertically from the earth in a column that would have overtopped the Eiffel Tower by nearly 250 feet and still kept rising. The fountaining began at 1:34 inches the morning, Hawaii Standard Time. It lasted 8.5 hours before the lava drained back from the vents and the crater floor settled into a new accumulation of cooling basalt. And the episode ended as all the previous 44 episodes in this sequence had ended not with a bang, but with a gradual cessation, a withdrawal, a silence that instruments measure precisely as ground tilt shifting from deflation back toward inflation. And then the scientists watching those instruments did not relax. They are watching something else now. Beneath the south rim of Halemaumau crater, in the week following that April 23 eruption, the Hawaiian Volcano Observatory recorded 30 shallow earthquakes magnitude 2 or smaller at depths between 0.6 and 1.8 miles beneath the surface. 30 fracture events in one specific zone in a single week at the shallowest levels of the volcanic crust. And the ground itself physically, measurably, in data captured by GPS instruments and tilt meters, rose by several inches along that south rim following the April 9 eruption episode. A discrete zone of upward ground movement in a location that is not one of the established eruptive vents. Scientists know exactly what that combination of signals means. They have seen it before, in this exact location. On the 6th of August, 2025, less than 9 months ago, the same composite appeared. The same south rim, the same shallow seismicity, the same ground deformation. What happened within minutes to hours of those August 2025 signals is the core of why scientists are on edge right now. A new crack opened in the earth. A fissure at a location that had not been an active eruption vent ripped through the south side of Halemaumau and lava began erupting from it. Not from the established north and south vents that have been the primary fountaining sites throughout the current 6-month eruptive sequence, a brand new vent formed with a warning window of minutes to hours. The USGS Hawaiian Volcano Observatory has now published its forecast for episode 46 of the current eruption. The window is May 3 through the 7th of May, 2026. The same precursory signals that appeared before a fissure opened 9 months ago are present right now, in the same location, exhibiting the same character. Whether the next eruption episode will erupt from the established vents, or whether it will once again open a new crack in the south rim, is a question that the science cannot yet answer with certainty. That gap between what the instruments show and what they cannot yet resolve is the precise edge on which volcanologists are standing. This is why the volcano that just erupted in Hawaii has scientists on edge. Kilauea is one of the most watched, most studied, most densely instrumented volcanic systems on Earth. It sits in a national park on the Big Island of Hawaii, beneath a monitoring network so comprehensive that researchers sometimes describe it as the most thoroughly observed volcanic system in history. Tilt meters measure ground deformation in real time. Seismometers detect earthquakes down to magnitudes that a human being standing directly above them would never feel. GPS stations track horizontal and vertical movement to sub-centimeter precision. Gas monitoring equipment measures sulfur dioxide and other volcanic gases continuously. Webcam feeds transmit live imagery of the crater floor and vents around the clock. All of that monitoring points to the same fundamental reality right now. The system is active, it is reinflating ahead of episode 46, and something specific is happening in the south rim that was not part of the ordinary eruption cycle. To understand why that matters, you need to understand what Kilauea actually is at this particular moment in its history, not as a general educational primer on Hawaiian volcanism, but as a specific geological system with a specific recent history that defines what its current behavior means. Kilauea is a shield volcano built above the Hawaiian Hotspot, a zone of anomalously hot mantle material rising as a thermal plume from the deep interior of the Earth. The Pacific tectonic plate moves slowly to the northwest over this fixed hotspot at roughly 2 to 3 inches per year. As the plate moves, new volcanic material accumulates above the hotspot, building islands. The Big Island of Hawaii sits directly above that hotspot right now, which is why it contains the two most volcanically active surfaces on Earth, Kilauea and its slightly older, larger neighbor, Mauna Loa. The character of Hawaiian volcanism is defined by the chemistry of hotspot magma. Basaltic magma rising from a mantle plume is low in silica and relatively low in dissolved volatile gases compared to the magmas feeding explosive subduction zone volcanoes. This makes Hawaiian basalt low in viscosity. It flows more like a thick liquid than a stiff one. When it reaches the surface, it flows and fountains rather than exploding in Plinian columns. There are conditions under which Hawaiian volcanoes can produce more explosive activity: lava contacting water, sudden pressure releases, phreatic events. But the baseline character of Kilauea's eruptions is effusive. It moves, it builds, it puts on a show. And so the public narrative around Hawaii's volcanoes has always carried a note of grandeur over alarm. Lava rivers glowing orange against a dark sky, helicopter tours booking out weeks in advance, tour operators selling seats above the crater for the cost of a nice dinner. The image of Hawaiian volcanism in the popular imagination is one of Earth's power expressed in approachable, spectacular terms. That image is not wrong. It is just incomplete. And right now, in the final days of April 2026, it is significantly more incomplete than usual. The eruption that began the 23rd of December, 2024, at Kilauea's summit has been running for more than 16 months. In that time, 45 distinct eruption episodes have occurred, each consisting of a period of intense lava fountaining, followed by a multi-day to multi-week pause during which the system recharges. The eruptions have produced lava fountain heights measured in hundreds of feet, sometimes approaching and exceeding 900 feet. The lava has been covering and recovering the floor of Halemaumau crater, with each episode reshaping the caldera landscape incrementally with each discharge. The scale of this ongoing eruption is larger than most public coverage has conveyed. The magma supply feeding these episodes is not diminishing. Tilt data shows the summit reservoir inflating at a sustained rate between episodes. The reinflation after episode 45 was rapid. The forecast window for episode 46, May 3 through May 7, was established quickly because the instruments showed the system recharging fast. This is not a volcano winding down. It is a volcano in full, sustained, active operation. And within that active operation, something unexpected is developing along the South Rim. To understand the South Rim signals, you need to understand the basic mechanics of how episodic eruptions at Kilauea actually work, the underlying pressure cycle that produces the regular alternation of eruption and pause. The summit of Kilauea sits above a network of shallow magma reservoirs, underground chambers, and conduit systems filled with molten rock under pressure. Magma is continuously supplied to this network from depth, fed upward from the plume system that drives the hotspot. As magma accumulates in the shallow reservoirs, it exerts pressure on the surrounding rock. Tilt meters on the surface measure the ground as it physically deforms under this accumulating pressure. When the summit inflates, tilt meters show an outward tilt from the center of inflation, the ground rising and spreading as the rock above the reservoir is pushed outward. This is the filling phase. When pressure exceeds the mechanical threshold of the weakest point in the system, which, under current conditions, is the established eruptive vents within Halemaumau, magma forces its way up through those vents and erupts at the surface. The episode begins. Lava fountains hundreds of feet into the air. The crater floor fills with new lava. The dramatic visual spectacle that draws visitors from across the world unfolds. Simultaneously, ground tilt deflates sharply as magma evacuates the shallow reservoir. When the eruption ends, the cycle resets. Tilt rises again as the reservoir refills. This pressure fill-release cycle is well documented at Kilauea. It is predictable in its general shape, predictable enough that HVO can issue eruption forecast windows based on the rate of inflationary tilt recovery. The filling rate tells scientists approximately when the reservoir will reach the critical pressure threshold again, giving them the ability to forecast the next episode within windows of days rather than weeks. But something is happening outside this understood cycle. The south rim of Halemaumau is not one of the established eruptive vents. The north vent and south vent, which have been the primary fountaining sites throughout the current sequence, sit within the crater floor area. The south rim is the wall of the crater, the structural boundary between the interior of the crater and the surrounding caldera surface. It is not, under normal operating conditions, where magma moves through. It has been experiencing the eruption as a structural witness rather than an active participant absorbing thermal radiation from the lava fountaining below, undergoing seismic vibration with each episode, and adjusting to the mechanical stress redistribution that occurs every time the reservoir below deflates during an eruption and reinflates afterward. The 30 magnitude, 2 and smaller earthquakes recorded beneath the south rim in the week following April 23 are occurring in this witness rock in a zone that is not an established conduit. At depths of 0.6 to 1.8 miles beneath the surface in a volcanic setting, earthquakes of this type and in this spatial pattern are caused by rock fracturing under pressure. In a volcanic context, the pressure causing that fracturing comes from one of three physical sources: magma physically moving into new crack zones and displacing rock outward, volcanic gases at elevated pressure migrating through newly opened fracture networks, or mechanical stress redistribution in the rock mass following changes in pressure conditions below. Each of these causes has a different implication for what happens next. Magma intrusion is the highest concern scenario because it means new molten material is actively entering a zone of the crust that was not previously a magma pathway, and if the intrusion continues, it may eventually reach the surface. Volcanic gas pressurization is also a serious concern because high-pressure gas in a shallow zone can create and propagate fractures, and sufficient gas accumulation near the surface can drive rapid, explosive activity when it finally ruptures through overlying rock. Mechanical stress redistribution is potentially the most benign of the three, but it is also the hardest to distinguish from the other causes based on surface measurements alone. The ground uplift of several inches measured along the south rim after the April 9 episode adds a critical second dimension. Localized ground uplift, the surface physically rising in a discrete zone, is not consistent with simple mechanical stress redistribution, which does not typically produce directional, upward-focused deformation of this character. Localized uplift is most consistent with mass accumulating beneath the surface at shallow depth. Something is moving into the rock structure and forcing it upward. The physical analogy is a blister forming beneath skin, pressure accumulating in a confined space below a surface layer, and the surface deforming upward because it has nowhere else to go. The combination shallow seismicity plus localized ground uplift in the same zone after an eruptive episode is a composite signal. And that composite signal is precisely what appeared before the South Rim fissure opened in August 2025. Not approximately the same, not superficially similar. The same signal type, in the same location, with the same character. HVOs. April 2026 Communications. The Volcano Watch article, published April 25, The information statement issued following the detection of elevated seismicity directly referenced the August 2025 precedent and identified the South Rim as a zone warranting heightened attention. The 6th of August 2025 Fissure event established a specific empirical precedent that now defines how the current signals are being interpreted. Episode 30 of the current eruption sequence began that day, with lava fountaining from the established vents within Halemaumau. During the final hours of active fountaining, HVO instruments recorded a cluster of shallow earthquakes in the South Rim zone. The warning window between those signals and the next event, minutes to hours. A fissure opened on the south side of Halemaumau, not at an established vent, a new crack, rupturing through rock along the stress zone the shallow seismicity had been indicating. Lava erupted from this fissure briefly before the episode as a whole ended and the system deflated. The event was short-lived, which is partly why it did not dominate the broader public conversation about Kilauea. But for the scientific community at HVO, it established something of profound operational significance. The South Rim can produce a new eruptive vent with a warning window of minutes to hours, and the precursory signature for that event is documented and recognizable. A fissure eruption is categorically different in its hazard profile from lava fountaining at an established vent. At an established vent, the hazard geometry is known, the location is fixed. The patterns of lava accumulation and gas emission have been observed across dozens of episodes. Safety exclusion boundaries can be set with confidence because the source of the hazard will not relocate. A fissure eruption breaks that certainty. Fissures can open anywhere along a stressed zone. The direction a fissure runs, which determines lava flow direction, ballistic ejector geometry, and gas emission source location, cannot be specified in advance because it depends on the microscopic mechanical heterogeneity of rock that no surface instrument can resolve. The moment the fissure opens, those questions are answered immediately by observation. But that is also the moment when emergency response must already be in motion. The 2018 Lower East Rift Zone eruption demonstrated the full-scale potential of Kilauea's fissure eruption mode. 24 fissures opened in the Leilani Estates subdivision. Lava buried more than 13 square miles of land. 700 homes were destroyed. Kapaho Bay, a beloved ocean snorkeling bay, was filled with lava and no longer exists. The summit context of the current eruption is different. The geometry does not replicate the Lower East Rift Zone pathway, and the direct lava flow risk to dense residential areas is substantially lower. But the principle is the same. A fissure eruption at a new location changes the geometry of every hazard calculation simultaneously, in real time, with the smallest possible advance notice. There is a layer of this situation that deserves distinct consideration, one present in the technical monitoring record, but not prominent in the public conversation about the current eruption phase. The South Rim of Halemaumau has been through 45 eruption episodes. Each episode subjects the rim structure to specific physical stresses, intense thermal radiation from lava fountaining hundreds of feet below, seismic vibration from the eruption activity, and the mechanical stress redistribution that occurs every time the magma reservoir below deflates during an episode and reinflates afterward. These stresses, individually, are not sufficient to cause immediate structural failure of rim rock during any single episode. But rock subjected to repeated cycles of loading and unloading, even below the level that would cause instantaneous failure, undergoes a process that materials scientists call fatigue. Fatigue is the progressive degradation of structural integrity under repeated stress cycling. Engineers account for it in every structural system designed to operate under dynamic loads: aircraft wings, bridge cables, turbine blades. The fatigue life of a component is the number of stress cycles it can sustain before developing the microcracks that precede failure. Rock is more heterogeneous and geometrically complex than engineered metal, and its fatigue behavior is correspondingly less predictable. But the underlying physics applies. A volcanic crater rim that has been thermally cycled and mechanically stressed through 45 eruption episodes does not have the same structural integrity at episode 45 that it had at episode 1. The shallow seismicity beneath the south rim may be detecting exactly this process. Microfractures forming progressively through 16 months of repeated stress cycling, accumulating until they reach a scale detectable as magnitude, 2 earthquakes. A zone of progressively weakening rock, and above that zone, the ground uplift, suggesting that something is taking advantage of the newly opened microfracture network to migrate upward toward the surface. The hazard this structural process represents is not limited to the Fissure eruption scenario. A crater rim section sufficiently weakened by fatigue can fail geomechanically, can physically collapse under its own weight into the crater below without requiring a new eruption to trigger the collapse. In the context of an active volcanic environment, structural collapse has its own severe category of consequence. Material from the south rim collapsing into the crater would encounter a thermal environment many hundreds of degrees Celsius above the temperature of the falling rock. Water contained in the pore spaces of the collapsing material, even small amounts would flash to steam essentially instantaneously. Steam at volcanic temperatures expands to approximately 1,700 times its liquid volume in an extremely short time window. If that expansion occurs beneath a mass of collapsing rock that temporarily confines it, the result is a phreatic explosion, a steam-driven blast that ejects rock fragments and ash at ballistic velocities in whatever direction the explosion directs them. The 2018 summit collapse sequence at Kilauea produced exactly this type of activity, repeatedly, over months. Ballistic blocks were ejected from the crater to distances that required rapid extension of safety boundaries. On the 3rd of June 2018, a steam explosion ejected a ballistic block through the roof of a geological observation structure within the national park that had been considered safe under the then-current hazard assessment. No one was inside at that moment. The current closure boundary around Halemaumau was calibrated around the hazard posed by the established vent configuration. It was not specifically designed for ballistic ejector from a phreatic explosion driven by south rim structural collapse because that scenario, while physically plausible given current signals, is a possibility rather than the baseline expectation. But it is a possibility that the shallow seismicity, the ground uplift, and the structural fatigue context of 45 eruption episodes together make non-negligible. 3 converging factors surround this geological situation, and each compounds the others. The first is visitor presence. Hawaii Volcanoes National Park is among the most visited national parks in the United States, and the ongoing summit eruption has consistently elevated visitor numbers throughout the current eruptive phase. The forecast of episode 46 between May 3 and the 7th of May 2026 is public. It appears on the Hawaiian Volcano Observatory website. It is covered by local media and shared widely on social platforms. The visibility of the forecast creates a predictable surge in park attendance during the forecast window as travelers make plans specifically to witness the eruption episode. This convergence elevated visitor presence during an eruption forecast window that carries an anomalous fissure risk is an operational challenge of real complexity. The fundamental problem is that the warning time for a new fissure opening, if one occurs, is the same as what was documented in August 2025, minutes to hours. Visitor management under normal eruption conditions involves orderly dispersal from viewing areas based on detailed pre-positioned response protocols. But an event requiring rapid expansion of safety boundaries in minutes, in a landscape where the specific new hazard location cannot be specified until the fissure opens, tests the limits of any protocol designed around knowable geometry. HVO, Hawaii County Civil Defense, and Hawaii Volcanoes National Park are actively coordinating around exactly this scenario. The people responsible for these protocols are professionals who have refined their eruption response roles over years of managing an active volcanic system under significant visitor load. Their operational plans are current, tested, and continuously updated. But operational excellence cannot close the gap between response time and warning time when a fissure opens with minutes of precursory signal. The gap exists. It is being managed as well as it can be managed, and it is real. The second convergence factor is the broader Hawaiian volcanic context. In April 2026, researchers published findings based on data from Mauna Loa's 2022 eruption that significantly advance the ability to forecast lava flow paths for future Mauna Loa events. Mauna Loa, the largest active volcano on Earth by volume, sitting on the same island as Kilauea, erupted for the first time in 38 years in November 2022. That eruption was relatively brief, but it demonstrated unambiguously that Mauna Loa is fully capable of reactivation after decades of quiet. The April 2026 research uses flow data from 2022 and advances in numerical modeling to produce substantially more accurate predictions of where lava would flow during future Mauna Loa eruptions, a genuine scientific advance with direct public safety implications, because Mauna Loa's flows can threaten communities on both the eastern and western slopes of the Big Island, depending on which rift zone erupts. Mauna Loa is not erupting. Its USGS alert level is at normal as of late April 2026. But the simultaneous publication of eruption prediction research for Mauna Loa in the same month that Kilauea's south rim is producing anomalous signals reflects a scientific community watching both major volcanic systems on the Big Island with heightened simultaneous attention. The two volcanoes share the same island and draw from the same hotspot. The nature of their subsurface interaction, whether activity at one has implications for pressure conditions at the other, is an area of genuine scientific inquiry that has not been definitively resolved. But both systems are active, both are under intensive monitoring, and both are producing scientific developments in the same spring window. The third convergence factor is air quality. Kilauea's eruption produces sulfur dioxide at rates that fluctuate directly with eruption intensity. Sulfur dioxide in the Hawaiian atmosphere combines with water vapor and sunlight to form sulfuric acid aerosols and fine particulate matter. The volcanic smog, known as VOG, that has been a documented public health concern for Big Island communities throughout the current eruption phase. During active fountaining episodes, SO2 emission rates spike sharply above baseline. Communities in the Kona and Kau districts experience the most direct VOG impact depending on prevailing trade wind patterns. Families with young children, elderly residents, and individuals with asthma, chronic obstructive pulmonary disease, or cardiovascular conditions make active decisions about outdoor activity and home ventilation based on air quality data issued in real time by HVO and Hawaii health authorities. If episode 46 involves a new fissure opening on the south rim, in addition to the established vents, the total eruption volume and total SO2 output would be correspondingly larger than a standard single-vent fountaining episode. A multi-source eruption means more lava being produced simultaneously, more volcanic gas being released, and a more complex atmospheric dispersion pattern for the vogue that follows. The communities downwind will experience this directly, in their lungs, in the quality of the air their children breathe, in the health advisories that interrupt their normal days. On the specific ground of the Big Island, the current situation resolves into concrete human stakes across several distinct dimensions. The immediate population at elevated risk is the visitor and park staff population within Hawaii Volcanoes National Park during the episode 46 window, concentrated near the crater rim viewing areas and along park roads adjacent to the summit caldera. Within the current established closure boundaries, that risk is managed. The escalation risk is what happens if the established closure boundary is not where the next eruption begins. A fissure opening on the south rim of Halemaumau, if it occurs, requires immediate assessment of lava flow direction from the new vent geometry. Lava follows topography. The south rim's elevation and orientation relative to the surrounding caldera landscape determines the flow path. That assessment cannot be pre-completed with precision because the specific location and orientation of a potential fissure cannot be specified until it opens. The Earth finds its own weakest line. Once found, the line is known. But that moment of knowing is also the moment when emergency response must already be executing. Chain of Craters Road and accessible sections of Crater Rim Drive. The infrastructure arteries of the park remain subject to ongoing closure adjustments based on evolving hazard conditions. A significant change in eruption geometry would trigger immediate reassessment of those boundaries, potentially in the middle of an active visitor management situation. For communities beyond the park, the direct lava flow risk from the current summit eruption configuration is low. The geometry of the summit caldera and the established eruption parameters do not support a scenario in which summit lava flows reach densely populated residential areas on current trajectories. The 2018 Lower East Rift Zone eruption threatened and destroyed communities through a specific plumbing pathway that is not being activated by the current summit phase. The community risk profile is dominated by VOG, real, ongoing, and scaling directly with eruption intensity and complexity. The most pressing open scientific questions in this situation are not theoretical. They are questions whose answers would change the hazard assessment and the recommended response posture for the agencies managing risk right now. The first is the specific cause of the post-episode 44 ground uplift on the south rim. HVO has stated publicly that the cause of this uplift remains uncertain. Distinguishing between magma intrusion, gas pressurization, and mechanical stress redistribution from surface measurements at depths of half a mile to nearly 2 miles in real time, without the ability to drill and sample, is genuinely difficult, even with the most comprehensive monitoring network available. The instruments are not inadequate. The physical question is at the frontier of what surface measurements can resolve. And the cause matters, because magma intrusion trending toward the surface has a different risk profile and a different time horizon than mechanical stress redistribution that may stabilize without further development. The second open question is the trajectory of the overall episodic eruption. 45 episodes over 16 months. The interval between episodes has varied from days to more than 3 weeks. Whether this variable interval episodic pattern represents a stable behavioral mode that the system will maintain, or whether it is a transitional phase, evolving toward more sustained continuous eruption. As the 2008-2018 summit lava lake phase demonstrated Kilauea is capable of, cannot be determined. From the current data, record alone, the eruption has not been running long enough, and the episode pattern has not been consistent enough to establish a confident trajectory. The 2008-2018 continuous summit eruption began with intermittent activity before developing into the stable lava lake configuration. The current episodic phase shares some surface similarities with the early stages of that historical sequence, but similarity of form does not establish similarity of trajectory. Kilauea in 2026 is operating in a caldera geometry that did not exist before 2018. The plumbing system beneath it was physically reorganized by the collapse. The system it is now is not the system that produced the pre-2018 lava lake, and extrapolating directly from that precedent carries significant uncertainty. The third open question appropriately flagged at the frontier of the science rather than established consensus is the nature and extent of subsurface interaction between Kilauea and Mauna Loa's magmatic systems. Historical and geological records contain evidence for inverse correlations between activity at the two volcanoes over certain time periods, Kilauea active while Mauna Loa is quiet, and vice versa, suggesting some degree of shared stress or supply dynamics. Whether those interactions are currently operating, and whether Kilauea's sustained 1-6-month episodic eruption phase has any implication for the state of Mauna Loa's magmatic pressures, is not known. The April 2026 research improved lava flow prediction capability for Mauna Loa. It did not address this system interaction question. That question remains open at the genuine frontier of Hawaiian volcanology. To understand where Kilauea is heading, it is necessary to understand where it has been specifically, to appreciate the magnitude of the reset that 2018 imposed on this volcanic system, and what that reset means for interpreting everything that has happened since. Before 2018, Kilauea's summit had been in continuous eruption at Halemaumau since March 2008, when a new vent opened and began degassing. By late 2008, that vent had produced a growing lava lake, a pool of active, convecting molten basalt on the crater floor. The lava lake grew and became a fixture of the volcano's behavior for the next decade, churning with the thermal convection of the magma column below, glowing red at night in a visual that became iconic for the national park and for Hawaiian volcanism broadly. By the time of the 2018 eruption, the lava lake had been active for nearly 10 years, one of the longest duration active lava lakes in the documented record of Kilauea. On the 3rd of May 2018, the bottom fell out. Fissures opened in the Leilani Estate subdivision in the lower East Rift Zone. 24 fissures ultimately ruptured across the residential landscape over the following weeks. Lava flows buried more than 13 square miles, destroying 700 homes, filling Kapoho Bay entirely, inundating the vacation land community along the coast. The Lower East Rift Zone eruption was one of the most destructive volcanic events in the modern history of Hawaii. Simultaneously, at the summit caldera 25 miles to the west, the Earth was collapsing inward. The vast magma reservoir beneath Kilauea's summit, the underground volume of molten rock that had been supporting the floor of Halemaumau and maintaining the active lava lake since 2008, was draining eastward. The magma was flowing through the deep conduit system of the East Rift Zone, feeding the catastrophic surface eruption in Leilani Estates. As the reservoir emptied, the rock above it lost its support. The floor of Halemaumau began dropping in a sequence of thousands of incremental collapses and associated explosions over the following months. Researchers counted more than 12,000 earthquakes at the summit during the collapse sequence, including dozens of magnitude 5 events. Each collapse produced a small explosive eruption from the crater as suddenly depressurized gas drove rapid steam and ash ejection. Ballistic blocks landed hundreds of feet from the rim. By the time the collapse sequence ended in August 2018, the floor of Halemaumau had dropped approximately 1,000 to 600 feet, nearly a third of a mile from its pre-collapse level. The lava lake that had glowed for 10 years did not flow anywhere. It dropped with the crater floor as the rock beneath it gave way. The reservoir that had sustained it was gone. The conduit that had fed it was abandoned. The configuration that had existed for a decade simply ceased to exist. The eruptions that followed are the direct consequence of this physical reset. The December 2020 lava lake formed in a crater that was 1,600 feet deeper than the one that had existed before 2018. The 2021 summit eruption operated in the same new geometry. The current episodic eruption phase, beginning December 2024 and now at 45 episodes, is filling a crater bowl that was carved by the 2018 collapse, a bowl that did not exist 6 years ago. Each episode adds new lava to that floor, gradually raising it back toward its pre-2018 level. That process, at current rates, would take decades to complete. As the crater floor rises, the geometry of the shallow magmatic plumbing system changes incrementally. Pressure relationships among the reservoir, the conduits, and the surface vents shift with each new lava accumulation. The system is actively adjusting its plumbing in real time, accounting for a physical geometry that is different after every episode. The repeated formation of new vents during this process, including the August 2025 South Rim fissure and the anomalous signals building toward episode 46, is what should be expected from a volcanic system still, finding its equilibrium in a caldera architecture that was reset just 6 years ago. This is not a volcano returning to a known stable state. It is a volcano in active geological reorganization, still solving for its new configuration. The South Rim signals are not anomalous in the context of this larger process. They are precisely what this process looks like at the scale of a single crater wall in a single week of monitoring data. Here is the question the evidence produces, stated plainly, without a comfortable answer appended to it. If the shallow seismicity and ground deformation on the south rim of Halemaumau continue to intensify during the current pause period, and if a new fissure opens during episode 46, with a warning window comparable to what was documented in August 2025, this will be the second documented fissure formation event in this specific zone within 9 months. 2 events in 9 months with the same precursory signature in the same location is not a statistical coincidence. It is the beginning of a pattern, and patterns in volcanic systems have geological meanings. What a repeated pattern of fissure formation on the south rim would suggest is that this zone is becoming a progressively more established pathway for magma to reach the surface. Repeated fissure eruptions in the same zone can, over time, develop into a persistent vent system. Magma that has opened a pathway once finds it easier to reopen the same pathway subsequently because the rock along that line has been thermally conditioned and mechanically modified by the previous passage of lava. Whether the south rim is on a trajectory toward becoming a secondary persistent vent system for this eruption phase is not yet established. 2 data points are not sufficient for confidence, but they are sufficient to document that the south rim is a zone of genuine, non-negligible eruptive potential, and that the precursory signals for south rim fissure formation are now specifically and empirically recorded in the scientific literature. The operational challenge this creates for hazard management is the challenge of planning for a hazard whose precise spatial expression cannot be specified in advance. Closure boundaries, emergency response protocols, visitor management procedures, these are all designed around hazard zones whose geometry is known or can be estimated with reasonable confidence. A developing secondary vent system on the south rim would require ongoing revision of those geometries in ways that cannot be fully pre-calculated, because the next fissure will not necessarily open in exactly the same location as the last one. It will open where the rock is weakest at the moment of the next episode's pressure peak. That location can be estimated within a zone. It cannot be specified to a point. The monitoring is as comprehensive as it has ever been. The scientific analysis is as rigorous as the current state of volcanology permits. The operational response is as prepared as any volcanic hazard management program in the world. And the gap between what is known and what must be planned for remains real not because of any failure of science or preparation, but because the physical question of where a specific crack will form in specific rock at a specific moment is governed by complexity at scales that surface instruments cannot fully penetrate. That gap is the operational reality. Managing it is the job, and the scientists and emergency managers doing that job are doing it at the absolute boundary of what is currently knowable. On the morning of the 23rd of April, 2026, 900 feet of lava rose above the floor of Halemaumau in the dark hours before dawn. It rose above the crater rim. It rose above the caldera walls. It rose higher than any structure standing on the island of Oahu. It lit the Hawaiian sky for 8.5 hours, and then it stopped. The system deflated. The tilt meters began their slow climb back toward inflation. The monitoring stations continued their continuous record of what the Earth below was doing. Beneath the south rim, the earthquakes continued. The ground remained elevated. The system charged toward episode 46. Kilauea is 300,000 years old. It was born on the floor of the Pacific Ocean, pushed upward by the same hotspot that built every island in the Hawaiian chain, adding layer on layer of basalt until it broke the water's surface and continued building. To its northwest, in order, Maui, Molokai, Lanai, Oahu, Kauai, Niihau, each one the eroded remnant of a former Kilauea. Each one carried off the hotspot by the slow movement of the Pacific plate and now subsiding, millennia by millennia, back toward the ocean floor from which it rose. The hotspot is fixed. The plate moves, the volcanoes are born, erupt, grow, and are carried away. The 2018 collapse was not a conclusion to Kilauea's story. It was a disruption, a geological reset, one event in a sequence that has been unfolding for 300,000 years and will continue long after every structure currently standing on the Big Island has returned to dust. The South Rim signals are part of that story. The shallow earthquakes are part of that story. Episode 46, coming within days, is part of that story. The scientists at HVO watching their monitors in the hours before dawn are part of that story too. Temporary observers of something ancient, working at the limit of what can be seen, doing the only thing that can be done: watch carefully, report honestly, and prepare as well as the science allows. Kilauea has been doing this for 300,000 years, and it is not finished.